on a project that was started and is still in progress basically, but it is worth presenting here. It basically, the title being the development and application of energy and exergy thermodynamic performance parameters to determine the amount of performance degradation of major components of a combined cycle plant. So here we go. Generally speaking, most plant operators tend to look at process parameter monitoring without basically realizing that this amount of data is very is useful, yes, and it has some value in it, but there is another step in which you can utilize the data to actually compute performance parameters, and this is where basically the project leads to. So here we go. Data required to calculate based on the energy and exergy analysis was obtained from the plant design heat and mass balance diagram. Manufacturers do not provide design performance parameters for components. They provide the overall plant performance. You can go on any one of the websites, General Electric, Siemens in particular, and you'll see that they provide us basic information on the overall plant performance. Individual component performance are not provided. So essentially the project required us to determine the design performance parameters on the basis of the energy calculations, or the first law energy calculations and the second law exergy calculations. So we look at the deviation between the actual performance parameters and the design performance parameters. So on the basis of energy and exergy. Following that, the results were used to determine the percentage degradation for each component, and the components with the greatest overall degradation were selected, and possible root causes for degradation and methods to restore their performance were discussed and proposed. The results were used to determine the percentage degradation of each component, and the components with the greatest overall degradation were selected, and possible root causes for degradation and methods to restore their performance were discussed and proposed. The results of the work can be used to implement a thermodynamic performance-based predictive maintenance program, which is again a further step on a process parameter predictive maintenance program for all the major components on this plant. And that is where the benefit is, so that a plant operator would have this program running whereby it actually computes the actual performance parameters, compare it with the design performance parameters to determine the level of degradation and performance. The object of this project was to develop and apply energy and exergy analysis to this combined cycle plant to determine the level of thermodynamic performance degradation. The plant basically consists of General Electric machines, 3 General Electric gas turbines with their associated 2-pressure heat recovery steam generators, which generate steam at 2 pressures to supply 1 GE steam turbine rated at 152 megawatts. A steam turbine in each block exhausts into air-cooled condensers. Figure 1 shows a diagram of the plant layout. So on this diagram, you'll see some of the major components. So for instance, we have here 3 gas turbine units exhausted into their respective waste heat boilers or heat recovery steam generators. And these HRSGs produce steam at 2 pressures. High pressure steam, the red indicates the high pressure steam flow, and the blue, low pressure steam, which is also supplied to the same steam turbine. So we essentially have 2 blocks of the same, and the steam turbine exhausts into this air-cooled condenser, and that completes basically the cycle. The condensate is returned back to the HRSG. So here we have, on the gas turbine, we have the major components being a big axial flow compressor, combustion section, and combustion gas turbine. The HRSG is essentially a two-pressure HRSG, and I think there's a diagram later on, I believe. Yeah, so the HRSG is a two-pressure HRSG, which generates steam at two pressures. And well, of course, the steam turbine is another major component. We have the air-cooled condenser, and the various pumps are also considered in this project. So this plant, as we said, shows all the major components. Another one of the more interesting aspects of it is that the gas turbine inlet temperatures are not usually measured, and we had to find a way to calculate it. So we had to develop a special method to calculate the gas turbine inlet temperatures. The design temperature was obtained from a specification sheet that they were able to obtain, but the actual temperatures, actual turbine inlet temperatures were not measured, and we had to find a method to calculate, develop a method actually to calculate it. And here we have the design and actual thermodynamic performance for calculating all major components on the basis of the first law. These were the various performance parameters that were calculated for the various components. Okay, so it's quite a long list. And as you can see, as I said, it is also in the presentation. Similarly, the first law, we did the same for the second law. In the case of the second law, we calculated the exergy effectiveness or exergetic efficiency, and the irreversibility or exergy destruction also calculated for each component. And so we were able now to compare the actual performance on the basis of the energy or first law analysis, and also on the basis of the second law analysis. And in so doing, we were able to determine the level of degradation in performance. So the percentage of degradation is computed for all the various parameters, all the various parameters that we considered for each component. And this is an example of the results that we obtained. It showed the gas turbine number 4 with the highest level of overall degradation, HRSG number 2, steam turbine number 2, air-cooled condenser number 1, low pressure heat pump number 2, high pressure heat pump number 1. So these were basically what we found from this work. Applications of the project basically will involve actually implementing a predictive maintenance program, which will help a plant operator identify the components which the major levels of degradation, and be able to schedule preventive maintenance before basically we reach a stage where it impacts negatively on the plant performance, or even actually resulting in a failure. So this is one of the major benefits of this in particular, and it would be nice to go to that next level where a predictive maintenance program is developed. So this basically is the basis of this project, and as I said, in relation to process parameters, operating parameters usually is what most plant operators use as a guide, and sometimes it may be misleading for many reasons. There's a situation, there's a particular case, for instance, on a gas turbine where on a hot day, the compressor performance is affected because of the higher ambient temperature of air. And we cannot basically use that as a guide to determine its performance. So the next step is to actually use the actual operating parameters and calculate various efficiencies on the basis of the first law, on the basis of the second law, and compare it with the design efficiencies and design performance parameters, so that you can actually see if there's any degradation. So if this thing is done in real time online, it means that you could actually trend that degradation or deviation in performance on the basis of both the first law and the second law. So you have basically two sound engineering methodology actually looking at degradation in performance, the first law and the second law. And therefore you will have a good guide in terms of determining the major components which are actually affecting your overall plant performance. A couple things just to note also, as I said previously, in relation to these design performance parameters, manufacturers do not normally provide those things. They are not available in terms of, let's say, for instance, the design isentropic efficiency of the compressor on the gas turbine. That is well known. It really runs between 85 to 89%. But the exact specific value is not provided by manufacturers. And the same applies to every single component. They give you an overall performance, overall plant performance in terms of power output, efficiency or heat rate at, let's say, basically ISO conditions, and you have to determine what your design performance will be at site, because of course your site condition is different from ISO. And on the basis of that, we have to calculate all the component design performance parameters. We have to calculate all the component design on the basis of the first law and on the basis of the second law, because we're basically using both laws in tandem to show and predict degradation in performance. And then based on data we obtain from the plant, we were now able to calculate the actuals. So we can now compare them with the design parameters and look at that level, the level of degradation. We were only able to do actual calculations for about 3 months. It is very rigorous and demanding in terms of the challenges that were involved in using actual plant data, because most people know that actual measurements are not as accurate to do proper analytical work. Sometimes you may end up with a situation where there's no mass balance on a component, and of course, in accordance to the first law, we must have mass balance in terms of inflows and outflows. And similarly, you may end up with an efficiency, an actual efficiency based on actual plant parameters to be better than design, and that is totally impossible. So these things sometimes point to errors in the instrumentation, which you have to rationalize and determine how you go around or get around that to be able to calculate the real actual performance. So this is one of the things that you have with plant instrumentation, the accuracy, and also the fact that sometimes they go out of calibration. So the mere fact that once you end up with an actual performance parameter being better than design, you know for sure that there is some problem with your data. So data validation is also another important aspect in terms of, and that is sometimes very, very challenging, I must tell you that. Other than that, the other thing was, one of the major achievements was to develop a method to calculate the turbine inlet temperature in the gas turbine. It's something which is not measured, it is not found in any textbook, and it's something which we worked on, and we were able to come up with a good method, sound method, to be able to do that, because of course it gave us good results. And as I said, the idea is to continue with this work to the extent where it can be done in real time with online computation, and such that it can be used to implement a predictive maintenance program. That is basically the major benefit of this project. Okay, so basically that's it in terms of what I have to say. The actual paper is it will of course be part of the proceedings of the conference, and therefore I want to thank you for whoever is listening. And if you have any questions, you could direct it to me or send it to my email, senen.matabadal@sa.uv.edu. Okay, is there anything anybody want to ask? Hello?
Hello, thank you so much, Mr. Matabadal, for your presentation.
Yeah, because what happened is that I never really used the system, so that wasn't really that prepared. Yes,
It's
go ahead.
okay, it's okay. We saw your presentation clearly, and we would like to thank you for that insightful presentation on the real-time monitoring of, I guess, plant performance. And I'd like to open up the floor for any questions from your colleagues, let's say in the Department of Mechanical Engineering. I'm sure they have comments and questions at this time. Are there any questions for Mr. Matabadal? I'm not seeing any in the chat. I guess at this time we have no questions.